All right, so here in 3.2, we're going to continue looking at t-distributions and making inferences based on t-distributions. Still just going to be confidence intervals and test statistics, but now we're going to look at situations where we're actually going to try to compare two different populations. So we're going to have two means, two sets of data, and all that kind of stuff. So the first way that we're going to look at this is actually something that we've done before. It's been a while. We're going to look at matched pairs situations. So I have here's kind of a summary to remind you what matched pairs are. So a lot of your quiz for this first part here for this section is going to ask you to determine whether or not you're looking at a true matched pair situation. Shouldn't be too difficult because you have learned about it before. So this part really is just review. So some key things when you're looking for matched pairs, you have to have the same variable measured in both populations. So you can't measure weight of one population and height of another population. They have to be measured the same way. And within the two data sets that we have, they need to be under two different treatment conditions. So a lot of times that'll be like a treatment and a control treatment. Okay, doing nothing is a type of treatment. A lot of times we look at like something, we measure we measure something before and after they take a certain product, or before and after they have a certain class. So the before would be one treatment, no treatment. The after would be after the actual treatment is imposed. And then matched pairs is called a blocking technique, if you remember that, and we use it to reduce variability. And the most important thing about matched pairs is the two subjects are paired and matched on as many characteristics as possible. And again, we can have situations where the subjects can be paired to themselves under two different conditions, though. So there are basically three key things we need in a matched pairs experiment. We need both data sets to be measured on the same variable. We need two different treatments to be imposed. One of those treatments can be a control. And then the most important one is that they have the subjects have to be matched to each other on as many characteristics as possible. And we actually list those characteristics. We can say we're going to match subjects based on gender and race and socioeconomic status or something like that. And then, of course, the other way that we can match people is we can literally match them to themselves, in which case they would be matched based on all characteristics besides the actual treatment. So those are really good. That's a really good practice to do. Okay. So now that we remember what matched pairs data is, let's go ahead and look at making the actual differences in matched pairs data. So the single variable in matched pairs data is always the difference between corresponding data points. So when we are making inferences based on a matched pairs experiment, we're going to be taking the data from one treatment and subtracting it from its matched pair. Okay, so there's actually a whole bunch of data on the back of this section here where you can see how that's done. So like on this one, we have students here that took two different exams. Okay, these are students are being matched to themselves. We're measuring the same variable, their exam score. Of course, they're weighted similarly, probably out of percentage. So in order to make an inference based on this data, we actually subtract the two exam scores from each other. And we can subtract it either way. I could subtract 2 from 1 or 1 from 2. We just need to make sure that we state that, because of course, with subtraction, order does matter. If I subtract one way, I'm going to get a positive number. If I subtract the opposite way, I'm going to get a negative number. So you can see, looking at this exam data here, at all of these differences, all of these numbers, these differences are positive numbers. So exam 2 minus exam 1 was always a positive number, which tells me that their scores improved from exam 1 to exam 2. Every single difference is a positive number. So they all had a positive difference. And those people that didn't have a positive difference just had no change at all. So those are the types of things that we're going to look at. And we're going to talk about how we can actually do significance tests and confidence intervals using this type of data. All right, so we're going to, wrong page. We're going to first make a histogram of the difference in temperatures on your calculator. So I'm just following what they did in Apex here. So if I grab out my calculator, I already have this data in. Again, this data is on the back of this section. We're looking at this data here. Okay, the only data that I need in order to be able to do a significance test or a confidence interval or any inference at all about the comparison between these two, I really only need the difference column, okay? A lot of times though, they won't actually give you the difference right off the bat. You'll have to calculate those themselves, which is no big deal. I can do 30 minus 6 is 24, 4 minus 15, 4 minus a negative 15 is 19, 40 minus 30 is 10. We can do that pretty quickly, but I also just wanted to quickly remind you that your calculator does also have the capability to do that subtraction for you, depending on how you have it. It does take longer to put these two columns in your calculator than it would to put just one column in your calculator. But just for example, if you already had this max and min data in your calculator and then you needed to compare the two, meaning you need to calculate a difference, go up and clear this out to show you how I did that. So again, if you already have this data in here and you need the difference data for some reason you don't already have it, you can go up and highlight this L3 once you have all that data in there, hit enter, and then I can literally tell my calculator to calculate L1 minus L2 or L2 minus L1, depending on what I want my output to look like. So I'm going to do L1 minus L2. Remember to get to the L buttons, they're in blue above our numbers. So I'll hit second L1 minus second L2. So now I have that my list 3 is going to equal everything in list 1 minus everything in list 2. I hit enter and it calculates all those differences for me at the same time. And since I do have that data given to me, I can scroll down and double check that, but you shouldn't have to. The only reason you would be putting this in this way instead of just manually putting in that third column without these first two columns would be if there was some other situation where you calculated something with these and then didn't have this data already. Okay, anyways, so going back up to what we have here, it says it wants us to make a histogram here, and there are directions on how to make histograms as well as box plots with your calculator on this page here. Okay, if you ever need to refer back to it, but I'll just show you real quick. It's super simple. We're going to go to our stat plot option by hitting second y equals. Turn your first plot on. We're going to choose the type that looks like a histogram. Remember, a histogram is a type of bar graph. And choose where your data is. Most of the time, your data will be in list 1. Right now, my data is in list 3, so I'm going to put second list 3. Frequency is, again, if you wanted your data to be repeated, if you wanted every data point to be in there twice or 3 times or so on. We pretty much always just leave this as a 1, though. So now I hit graph. And it looks kind of weird because my window is not set correctly. Remember though, your calculator does have the option to set your window to what it believes will be the best way to view statistics. And that option is zoom. Option 9 is zoom stat. You can just click the number 9 to go there from your zoom menu and it zooms out to the perfect spot here. So I'm going to go ahead and since they asked for it, I'm going to actually sketch that picture right here. So I've got a couple bars that are the same height, one that is taller, one that is slightly shorter, and then I have one way over here that is even shorter than that. Oops, I put that in the wrong spot. Let me see if I can fix that. Doop. Copy. Delete. I was like, I just hit cut, huh? Paste. Oh, come on. Way up here. There we go. So there's a histogram. I would probably add some numbers to this, and which I can do by hitting the trace button and moving side to side. This looks like it's where we have, this is between 4 and 11, between 11 and 18. I'm mainly interested on this outlier, 46. All right. So 46 appears to be an outlier, okay? So we need to confirm, is this an outlier or not? Because in a lot of our situations here, in order for us to perform significance tests and to create intervals, we have to make sure that we don't have any significant outliers or skewness occurring. So we're gonna determine if this is truly an outlier or if it's close enough that it's okay. So there's two good ways to check to see if something is an outlier. The first and probably the easiest way to do it, since I already have my data in my calculator, I can go back to my stat plot and change this to a modified box plot. That's the box plot option with the dots on it, meaning not only is it going to show me my min and my max and all of that stuff, but it's also going to put dots where I have outliers. This option will not put dots where you have outliers. So I'm going to choose that one and regraph my plot. And you can see, yes, indeed, 46 is an outlier. And so I'll sketch that as well. So 46 is an outlier. The second way we can check to see if a value is an outlier, going back to like unit 1, we still have to know how to do it that way. Remember, to calculate an outlier, and it's defined as either your third quartile plus IQR times 1.3 or your first quartile minus 1.5 IQRs. Okay, this apparent outlier here is on the upper bound, so it's above my third quartile. So I'm going to look here to see if 46 is greater than that. And again, since my data is already in my calculator, I can get those quartiles and the IQR very quickly by going stat calculate 1var stats. And if I scroll down, I can see my median is 19, my first quartile is 13, and my third quartile is 22. So this would be 22 plus 1.5, and the IQR, remember, is the third quartile minus the first quartile. So when I calculate this, we get 35.5. So again, that means anything greater than 35.5 here is an outlier, and 46 is definitely greater than 35.5. So 46 is an outlier. Okay, that's not all though. It also asks you here, does the outlier have a strong effect on the distribution? So here you have to remember, when an outlier is not necessarily always a bad thing. Okay, when we do have outliers, a lot of times we can just ignore them if they don't have a strong effect on the distribution. If they do have a strong effect on a distribution with strong effect, will pull the mean away from the median and towards the outlier. Okay, so we saw like samples like this, or maybe there'd be an outlier out here. The median would be maybe over here, and the mean would get pulled towards that outlier. Okay, and the more influential that outlier is, the further it pulls the mean towards itself. So I already have those 1var stats calculated in here. The median is 19, and the mean is 18.77. It was almost like the same. Make sure that's an M. M is, what did I say, 8? Did I say 19? Gosh, I forgot. Yeah, 19. So those two numbers, oops, 18.77 and 19 are extremely close together. So it looks like the one is being pulled a little bit one way, but they are so close together that I would say this outlier is not very influential. Okay, so the outlier is not influential. So that means that we can go ahead and just ignore it and continue as normal. All right, so let's go ahead and talk now about how do we actually calculate or create confidence intervals for this paired data. Okay, and for this, remember we have this from the last section. We take our point estimate and add and subtract our margin of error, which will be our T star, which is dependent on our degrees of freedom and the area or the level of confidence that we want, with our sample standard deviation called our standard error, divided by the square root of n, or our sample size. So let's go ahead and use that. So basically all we're going to do here, since we have matched pairs data, is that these statistics, the X bar and the S, are now going to come from the differences. They were sort of that third column where we subtracted the data. Other than that, there's really no difference. So if I go back to what I had here, so again, or no, yep, were we looking at the same data? Yes, we are. Okay, good. So again, this was the 1var stats for my third column, my third list, which gave the differences in temperatures. It was the difference of two lists. So my X bar is 18.77. So I'll write this down, 1var stats. Gives me everything that I need. X bar is 18.77. S sub X, our standard error, or not a standard error, standard deviation of our sample is 8.32. N is 30, which also means that our degrees of freedom is 30 minus 1, or 29. Okay, and then the last thing I need to be able to do my confidence interval is my T star, which we're going to get from looking at our T table. So in our T table, I'm going to look for degrees of freedom 29. And let's see, what would my upper tail be for a 95% confidence interval? So 95%, when we 5% goes in both tails, half of 5% is 2.5%. So we're going to look in our table for where the degrees of freedom 29 intersects with the area 0.025. And once again, in our T table, it actually gives the confidence levels at the bottom here. So I don't even necessarily need that tail area. Just don't always count on T tables having that confidence level listed for you at the bottom. So we're looking at a 95% confidence level with a DF of 29 here. And so that intersects right here at 2.045. So our T star is 2.045. 2.045. And again, that was from our T table. All right, now we have everything that we need to calculate our confidence interval. So we'll go ahead and do it just again using this equation right here. X bar is, I'll write actually X bar in. X bar is 18.77 plus or minus T star, which is 2.045 times S, 8.32, divided by the square root of n, which is 30. Okay. And at this point, I just get out my calculator and start punching in numbers. My margin of error, 2.05 times that fraction ends up being about 3.11. So when I subtract, I get the lower bound of my confidence interval, 15.66. And when I add, I get the upper bound of my confidence interval, 21.88. Okay, and that's it. Doesn't tell us to interpret it, so we can move on. Okay. So now let's go ahead and look at significance tests on this matched pairs data. So with significance tests on matched pairs data, they're the same as they are for single samples. Our data points this time are now just the differences in the data points of two different samples. So each data point now is going to be either x1 minus x2 or x2 minus x1, depending on the order which we want things to turn out. So our null hypothesis now is actually going to be the mean of the difference in two data points. And what would we want the mean to be? Well, in a null hypothesis, we are supposing that the mean of one sample is equal to the mean of another sample. So in our null hypothesis, again, we're assuming that there is no change from the norm. Everything is just normal. So applying a treatment changes nothing. So we would expect the two groups to have the same result. Nothing would get better, nothing would get worse. It'd be just the same. Okay, so if I subtract these two things that are equal from each other, we get 0. So for matched pairs data, when we are doing a significance test, H naught will always be that the difference is 0, meaning there is no difference between the two sets of data where two different treatments are imposed. Okay, and then from that, of course, we can hypothesize that maybe there is a difference. So if we expect the results to increase, and actually I should write this differently here. It makes more sense if I put x2 first and then x1. Okay, if I take my after results and subtract the before results, if things have improved, then that number will be positive. Okay, we saw that in our test scores. The test they took second minus the test score they had first, when I subtracted them in that order, all of those numbers were positive, indicating that their exam scores had increased. Okay, if they had done worse in the second exam, then we would see negative differences, so less than 0. And we can, of course, also talk about two-sided differences or two-sided tests here, where we're not necessarily saying that it's greater than or less than, simply that it's just not equal to. And if they're not equal to each other, then we're just going to say that the difference is just not 0. Okay, so we still have all three tests. We just have to consider what type of difference we are looking for. So let's perform a significance test to determine if those stats students' exam scores improved from the first to the second exam. And when we looked at it, every single one of those scores was a positive number. So I'm betting that we can say yes. Let's go ahead and do the test though. So we know with the significance test, we always start by listing our conditions to make sure our conditions are met. So with our conditions, let me actually look here real quick. No. So with our conditions, if our sample size is larger than 30, then we can have a significant amount of skewness and or some outliers, because t-tests are robust, right? We learned that in the last section. But when our sample size is small, we have to be careful. We can still have a little bit of skewness, but we want to make sure there's no extreme skewness and no outliers when our sample sizes are small. So in this case, our sample size is 24. And again, I'm looking at this data here, 24 students. Okay, so my sample size is 24. Which is small. So we have to check this data for skewness and outliers. And since this is notes, I'm going to write a note here that says we must check for extreme skewness. Doesn't have to be perfectly normal, but it can't have any extreme skewness or outliers. Okay, so when we're doing this here, we are going to be using a calculator for a lot of this, and we have all of the data in front of us. So we're going to go ahead and put that list into our calculator to check for those things. And I, of course, already have done that. I hit it over here. Oh, no, I didn't. Where did it go? Oh, I thought I had it. Oh, okay. So I just put in the differences here. So I'll go ahead and clear that out since I'm done with it. So right here, I have the differences from that third column right here. You can see. Also, one thing I wanted to note, I put all my data into this lists. I put this column, exam 2 minus exam 1, into my lists, knowing that there was supposed to be 24 pieces of data, and I ended up with 25. And the reason why I ended up with 25 is because this one here is part of the title, the category. It's exam 2 minus exam 1. That's not a data point, and that got a little confusing. What tipped me off was the fact that there is no corresponding data for that one. So we start with 0, not with the 1, to get those 24 pieces. And again, they gave me those differences, so I just put them in there just like that. Okay, so now I'm going to go ahead, and again, the easiest way to check for outliers and even just skewness is a modified box plot. So I'm going to go second stat plot. I already have the modified box plot selected here, so I'll just change this to list 4, which is where my data is on this question. And I hit graph. I'll probably need, I'll need to adjust my zoom. Zoom 9 is the stat option, and I can see right away there are no outliers, and that looks pretty symmetrical. So I'm going to sketch that into my problem as my way of showing my work. And it is just a sketch. So there is no outliers or extreme skewness. So remember again, with all of these different tests and procedures that we do, almost all the time, there are conditions that have to be met in order for us to perform these tasks. And so you always have to make sure that you are checking to make sure those conditions are met before you even start. Okay, so now that we've checked that, we can go ahead and start. So we always start by just stating our hypotheses first. So like I said before, our initial hypotheses will always be that the difference, which how are we doing our difference? Got to make sure we do it in the right order. Let's see, it's exam 2 minus exam 1. So let's label exam 1 x1, and we'll label exam 2 x2. Okay, simply by writing x1 and x2 in these areas, I have indicated that x1 is the data points from exam 1 and x2 is the data points from exam 2, which means that my list that I'm looking at data is x2 minus x1, not the other way around. Okay. So we're going to do x2 minus x1. And of course, our null hypothesis in matched per situation is always that that difference is 0. It will never be anything different. Okay, but I need to put that in context. So in context, we will say there is no difference. Or actually, I can say this even easier. The exam scores did not improve. And then our alternative hypothesis, what we are hoping for, is that the exam scores did improve, which would mean my second exam score is higher than my first exam score. So when I subtract them in this order, I will get a positive number, meaning the exam scores did improve. Okay, so that's step 1, written in formula form and in context. I'm writing way bigger than I did on my page here, so hopefully you're keeping up. And then we go ahead and we do our significance test. So I would write, we will perform a 2-sample t-test with alpha equals 0.05. And they give that in Apex. They say to use 0.05 for this problem. All right, so let's go ahead and do that. So we calculate our t statistic, which is the same thing as a z statistic, except we're going to use S instead of sigma. Okay, so we need some things to be able to do this. I need X bar, and I need S, and I need N, as well as, I suppose, the degrees of freedom. Okay, so since I already have my data in my calculator, let's go ahead and do 1-bar stats to get X bar and S, as well as N, even though we already know it's 24, which means degrees of freedom is 23. So I'll go stat, calculate one var stats. We're in list 4 this time. There it is. My X bar is 4.75. My S is 2.80. And again, my N is 24. It's also in one var stats, but we already knew that. So I'll calculate this X bar. Actually, I'll write it out in formula form for you first. X bar minus our null hypothesis divided by S over root N. Okay, so our X bar is 4.75 minus the null hypothesis that the mean is 0. So these are very easy to calculate. S is 2.8 and our N is 24, which gives us about 8.24. And when I use that to calculate my p-value from my table, so from my table, I'm going to look for 8.24, 8.24, where the degrees of freedom is 23. Oops, wrong way. 8.24 and 23. So let me real quick erase. Ooh. So we're looking at degrees of freedom 23. So we're only looking at, that's a really big, but 23, the middle one there. I don't know how to make it smaller. And we're looking for 8.24. So in 23, 8.24, well, it only goes up to 3.76. So this is far beyond that. Okay, which means our p-value is going to be something less than 0.0005, which already tells me it's low enough to reject our null. But if I needed to get an exact p-value, since we cannot with our table, we would need to use a calculator. So let's go ahead and do that. I'm going to go back to my page here. So even with the table, since even though it's not on there, we can tell for sure that our p-value is going to be less than 0.0005, which means it is definitely less than our significance level, 0.05. So we can reject our null. We can make a conclusion here, even with just that table. But let's go ahead and use our calculator since we have it to get our exact p-value. So to do that, I will go TCDF. And actually, I'll give you a note here. This is not on the table. Not on table. We're going to use TCDF from 8.24 to a really big number with degrees of freedom equal to 23. So I'll grab that and show you. Second distribution, TCDF is option 6. My lower is 8.24. My upper is a huge number. And my degrees of freedom is 23. So my p-value, again, this is in scientific notation. This E-8 over here means I'm going to take this decimal and move it 8 places to the left. So it's going to be 0.1234567 zeros. And then the number 1. Oops. So is that less than alpha? Yeah, we already knew that was going to be less than alpha. So we can reject our null hypothesis. So last thing is to write my conclusion. Since our p-value is less than alpha, we reject H naught. Okay, and now I have to put that in context. What does that mean? That means there is evidence, and in this case, there is strong evidence because our p-value is super tiny, that HA is true. And what was HA? The exam scores did improve. All right, and that is it for 3.2.